Hello and welcome to a new tutorial about conifer tools. Today I'm going to talk about how to create inductor spiral components using Python MCell library. In this folder I have a technology file that we have already spoken about. If you don't know how to set up this file, you can see it in one of my previous videos. Here I have Python scripts. First part of the Python script is to activate license file and to set up technology file. Next part is to use function from MCell library to create inductor spiral component. Here are the parameters of the function that I'm going to use. First, we can specify number of parallel jobs that are going to be used by the function. This is relevant only if we do sweep with this function. But if we create only one component, it will use only one thread. Then we have GDS file name, we have cell name that is inside of GDS file. We have a plus pin name, minus pin name, metal stack. Metal stack can consist of one metal layer, but two metal layers can also be used. Then we have winding width, space between winding, underpass, metal width. Then we have diameter in X direction and diameter in Y direction, number of turns. Number of turns are specified with a step of 0.25. There is a pin length, pin spacing. This pin spacing is relevant only if plus and minus pins are on the same side. Otherwise, pins will be centered in the middle of the geometry. Then we can also do a dummy fill. If we specify these numbers here, default number is -1, which means it will not do any dummy fill. I can specify these arguments at the end of every of these functions. For example, I did it here, and these dummy fill numbers are relative in respect to diameter. So for example, if I put here 5, it will do dummy fill 5 microns more than diameter in each direction. I will first create a folder inductor, and then in this folder I will save several of these components. Here is directory in which I'm running the script. So the script can be run like this. What we can see is that we have inductor folder. And for the first one is rectangular TM2, which means it is using top metal 2 layer. I can open it in key layout, and it looks like this. This is plus pin, this is minus pin, this here is pin length, here is the pin length. We see a number of turns, here is 2.5. This is diameter in Y direction, this is diameter in X direction. We have metal width, and we have metal spacing here. Second thing that we can do, instead of giving only a top metal 2 layer and name of the metal layers that you can use, they are specifying the technology. Here I have top metal 2. Adjacent metal layer is top metal 1, so I can specify top metal 2, top metal 1 with column. This means it will use 2 metal layers connected with wires to produce our cell. So this is, for example, this one. As you can see, it is not only one metal layer. We have top metal 2 layer, then we have wires, and below we have top metal 1 layer, and this is something that you can see like this, and then it is connected to the metal layer that is below top metal 1 layer. This is metal 5. And in this case, because minus and plus pins are on the same side, Pin spacing is basically spacing between these 2 points, middles of these 2 metal lines. We can also have octagonal geometry. This is octagonal geometry. Function is very similar like these 2 functions. The only difference is that we use octagonal geometry here. And then what I can do also, I can specify those 2 last arguments for dummy fill, and then cell would be populated also with the dummy fill, as you can see here. I will hide all metal layers. These are boxes that are usually logical layers. They are going to say something like, do not do any kind of automatic dummy fill in this area. Then I have here metal 5, as you can see. I made this cell in metal 5, and metal 5 is also used for dummy fill. As you can see here, this is how dummy fill looks like in metal 5 layer. It will not populate parts where you already have some elements. It will just do dummy fill around. And this structure is DRC clean. Then there are here vias between metal 5 and metal 4. So this is metal 4. In metal 4, you can see here the complete minus pin is in the metal 4 layer, and that's why dummy fill is not done in this area. And then you can see other dummy fills. For example, this would be metal 1, and then next to it you can see metal 2 dummy fill. And then we might have some box around it, and this type of dummy fill is applicable to all functions that I'm going to show today. Next, I will comment this part, and then I will show you how you can do sweep. All of those functions are also supporting sweep option. Sweep means that I can specify some of those parameters with start value, stop value, and step. So for example, for this option, it will take values 4 and 6. For this one, it will take value 2 and 4. For this one, 4 and 6. For this one, it will take from 2 up to 4 with step 0.25. And this function will generate all of those components in folder inductor sweep. I can run it again here. You can see there are together 288 components. For some components that are not feasible, you will see here warning not feasible. For components that are feasible, you will see this done argument. Now we can go inside and look inductor sweep. So you can see, for example, here we have many different geometries. Every single geometry will have name, underscore, and then values for all of those parameters that are defining that geometry. That's why when you are specifying name for this kind of component, you should never use underscore as a part of the name. Now we go to next component where we can do tapping. Tapping means that there will be one more pin that is called tap pin. So we have tap pin name, and we have tap pin width, tap pin length, and we have a number of turns after which tapping is going to be done. So this number of turns always has to be smaller than the number of turns that is given here, and this argument needs to be done in a step size of 0.25. Now I can run the script again. We have two options. One is rectangular and the other one is octagonal. I'll go here and open octagonal. As you can see, we have one more pin here, and now we have 3 pins. And in case of rectangular geometry, we also have one additional top pin. Next option that we have is components with a shield. This is pattern ground shield that can be placed below a component itself, and it can reduce losses. We have also here some additional arguments. Shield pin name, in this case it is called ground, and shield metal stack. So I'm using metal 1 for the shield. Then at the end we will have shield in X direction, shield in Y direction, width of the fingers and spacing between fingers for the metal shield. We can run this function as well. First, we have octagonal option, and then for octagonal geometry, we will have also octagonal shield. You see here, I have standard component, and then below this component in metal 1, I have shield. And this is how it looks like. Then I have also rectangular option for rectangular geometry. Shield will be also rectangular, and again we can see we have a standard component, and then below the standard component we have metal shield. So this argument here, which is shield X, actually this is the length here between diameter and the shield on this side. This is the X direction. Those two dimensions are the same on the left and on the right side. And then in Y direction we also have this dimension here, length on upper and lower side, and they are always the same. Then at the end there is also option that combines shield and tapping. I have to give information about shield and information about tapping, and as well I can give information about dummy fill at the same time. And if I run the script, we will get output here. So that is octagonal geometry. We can see we have here a cell with tapping, and then below that cell there is a metal shield, and we have the same option for rectangular geometry. So metal shield below and cell with tapping option.